All right, section 2.3, we're actually going to think about section 2.2. So if you still have 2.2 notes out, that's great. If not, try to keep them at your fingertips because we're going to look back at some of those pictures that we drew to make some claims about what's going on. And we're going to start on that right away. All right, so take a look at the graph where you had something that looked like f of x equals a constant. What did that graph look like?
Straight line.
It's a straight line. And when you say straight, what do you mean? Can you be more specific? Horizontal, perfect. So here is a horizontal line. What in the world happened on the graph, and it was a piece of a graph, where we had horizontal lines? What happened to the slope? We got a slope of 0, right? The slope on this graph is 0. So when we're talking about taking a derivative of a constant, it's actually 0. This was the piecewise graph where we had a couple of sections where they were flat, and we ended up on the x-axis, right? Because the slope is 0. So when we have a constant that is a single number, no variable attached to it, like f of x equals 7 or 3 over 2 or something like that, and we want its derivative is 0. Because the slope of a constant graph is no slope. It's a 0 slope. All right. There's one missing in here, and so I'm going to write it in. I don't know that it's probably missing because it's not specifically stated in your book, but it usually is stated. So we're going to do linear as our one that's sort of missing in the middle here. The linear rule says something like this. If you have a function f of x equals, I'm just going to write it mx plus b since that's one of the ways you're used to seeing that written. All right, so take a look back at your graphs. There's a graph that you had that was a diagonal line, right? What happened when you took its derivative? The picture. It was a diagonal line. What did its derivative look like? It looked like a horizontal line, right? So the horizontal line, has no slope, right? It's a 0 slope, and it's a constant value. Now the constant value is actually the value b, wherever the slope intercept, wherever the y-intercept was, I didn't say that right, is m, whatever the slope was to start with. Let me get the right letter in there. Whatever the slope was to start with. And now that should make sense, because the derivative is just the slope. What's the slope of a line? Well, the m in the formula, right? So you just get whatever the slope was. So if you took a horizontal or took a diagonal line and you looked at its slope is actually defined in the equation of the line itself, and its derivative ends up being a horizontal line at that height. This is f prime of x is equal to m. All right, now there's a couple of them in your notes from last time where it looked like a graph of a cubic. It was the first one we did. I think it was number 3 when we did it. And when it started out looking like a cubic, that is something that looked like x cubed, its derivative ended up looking like something that was quadratic. Quadratic formula looks like what? X squared. And then we had a graph after that where it looked like a graph of x squared. And one of the ways, in fact the way that I drew it, made it look like a line. And a line ends up having a graph that has just plain old x in it. I mean, it may have mx plus b, but it doesn't have any powers. This is related to the power rule. The power rule says that if you have x raised to the n power, then its derivative is n times x to the n minus 1. So the exponent becomes the coefficient of the x, and the exponent is now 1 less. Now, I'm sort of drawing yourself back into the fact that we had these nice images that looked like graphs of things to sort of verify that this is working. We could do this also if we looked back into section 2.2 or 2.1 where you were doing things with that limit definition. We had an example where it was a cubic example. In fact, I think the cubic example looked something like x cubed. In fact, it had a piece of x cubed in it. And when we took its derivative, we actually got 3x squared. But we did a lot of work to get it, right? So we put that h in there, and we multiplied things out, and then we subtracted f of x off, and then we divided by h, and then we took a limit, so we had some algebra, and then we plugged in 0 for h. You guys know what I'm talking about, right? That was in section 2.1 and in 2.2. All of that gave us the same result, that this is 3x squared. So what I want you to understand is that these formulas are coming from that definition. Right? So if you do something enough, if you did that limit definition enough with x squared, eventually you would look at this and go, you know what, every time I do this thing that starts out x squared, it becomes x. Every time. I wonder if that's a pattern. I wonder if that always works. And the answer is it does. So these are general rules based on that limit definition. That's where they're coming from. The other two pieces of information here are also very helpful. They tell you that if you have a constant in front of a function, like c times g of x, that constant c remains part of the derivative of the function. I'll show you how that works. This one, when you see it happen, you don't even realize you're doing it. I mean, you just are like, how did I use that rule? Well, you did. And so I'll show it to you. Like, I will verbally tell you, hey, look, we used this rule here, and you didn't even realize it. So this one's one that you use all the time and don't realize it. And so is the last one here, the sum and difference rules. All this says is that if you have two different functions and they're added or subtracted, that you can take their derivatives individually. And whatever you were doing to begin with, whether it was addition or subtraction, the result will hold true with addition or subtraction of the derivative as well. So what that allows us to do is it allows us to take each different piece of our function and do its derivative separately. And that's a very, very cool feature, and it only works with addition and subtraction. Very quickly, as in today, later, we will show that that doesn't work for multiplication or division. So the fact that this is working for addition and subtraction is a great thing, but it doesn't just generalize to every operation. All right, so let's talk about this particular one. First example. We're going to be using that sum difference rule right off the bat because you see three different pieces separated with addition and subtraction. Agreed? So we're going to do three separate derivatives, one at a time. Now we have we learned three different notations primarily. We can use either one. We can either call this y prime, or you can call what you're about to do dy dx. So give it one of those two names at the beginning. My default usually is to use the prime notation, and when I need the dy dx, I'll use it, but I don't need it right now, so y prime's quicker to write. I'm lazy, okay? So I'm going to use y prime. So you choose your favorite, and then we're going to do the x to the 7th. Okay, so x to the 7th is a plain old power rule. I have a power of 7, so what's going to happen to the power of 7? It's going to come down and become the coefficient. And then the power of 7 will become the number 6, one less. And that's it. Do you miss h's and limits? No. Okay. If you had to do this one with h's and limits, it would be quite lengthy because you'd have to multiply x plus h by itself 7 times, right? That would not be fun. All right, how about the 3x? The 3x is actually that linear rule that I sort of threw in here that your book kind of leaves out. It's 3, right? The nice thing about 3x is it's a line with a slope 3, so derivatives are the same thing as slopes. So this is just 3 here in the middle.
That still technically follows the power rule.
It does. It does. And you can think about it that way as well. So you can think about the fact that this is 3x to the 1. The 1 gets to be multiplied basically by the 3 at the beginning, so it gives you 3. And then the new power is the power of 0. Anything raised to the 0 power is 1. You can think about it that way. It's probably a little bit more conceptual work to do it. But yes, it does still follow the power rule. You're right. All right, this last piece right here does not look like any of the rules as it's currently written. Do you agree? None of my rules said anything about what to do when I had fractions or division, which is really what's going on here. However, it can be rewritten. This piece right here can be rewritten as 4x to the negative 1. Right? X in the denominator can be pulled up to the numerator. And when you do that, you change the power. This had a power of 1. So you change that power to have a negative of that power. That's a property of exponents. Everybody good with that? All right. That's really good because that looks like a power rule now, right? I'm going to put this in parentheses just to emphasize what we're doing. When we're in the middle of doing this, we're actually going to be using that coefficient rule, constant multiplier rule that we had there toward the end. Because what you're really going to be doing is you're really going to be taking that negative 1 as the exponent and you're going to be bringing it down. And you're going to be multiplying it by the 4 that's already there. The 4 doesn't change. It's just part of the answer. And that's what the constant multiplier rule says. So I have 4 times negative 1, which gives me negative 4. And then I need to decrease the exponent by 1, which means it will become negative 2. We're going to do one step to rewrite and clean this up. Obviously, the first two pieces don't need any cleanup. However, the second one I've got minus and negative, so we'll change that into plus. And if the problem did not start out with negative exponents, it needs to not end with negative exponents either. So we're going to put that x to the negative 2 back down in the denominator as x squared. There's absolutely nothing wrong with negative exponents or fractional exponents, but we're just going to mimic whatever the problem started as, the problem should look like when it ends. And there's your derivative. Wow.
That's beautiful.
It is beautiful, isn't it? Shall we try another one?
Yeah.
Okay. Now, what about this one makes what we've done so far not look like what we've done so far? There's multiplication, right? You guys see the multiplication. I've got some parentheses. Now, I mentioned this already. I'll mention it again. You cannot take the derivative of each of those pieces and then multiply them. And I'm going to show you why shortly. We're almost there. Okay? Which means at this point, what would you have to do this problem? FOIL. We need to multiply it all out. Okay? And to be honest, this one's simple enough to multiply out that even once I have another way of doing this, foiling is still probably the simplest option here. Okay? So let's multiply this out. The first terms I get what? Sorry, this is not a derivative yet. Let me take that off. 3x cubed. My outside terms give me the x and the negative 4, so that's negative 4x. On the inside, I have 1 times 3x squared, so this is 3x squared. Yeah, I just saw that myself. There we go. Fix that. And then the last two terms are 1 and negative 4 to give me negative 4. And if you're a little OCD, and I am a little OCD, I kind of like to put this in order. You don't have to. I'm going to be okay if you don't, but I have a tendency to do this. So I'm going to write it this way. Just to make me feel good. That's all. Okay? Did I switch them again? Did I screw something up?
No.
Okay. So we're all good?
Yeah.
Oh, good. All right, you ready to do a derivative?
Yeah.
Excellent. You had no idea it was a little OCD, did you? You couldn't pick up on any of that already, have you? Figured. All right, we have 3x cubed. What are we going to do?
Power rule.
Power rule. So the 3 that's the exponent will come down and get multiplied by the 3 at the front to give me a grand total of 9. And my new exponent will be a squared or a 2, right? 3x squared, what am I going to do?
Power rule.
Power rule again. So what am I going to get? 6x, you bet. How about negative 4x? What will happen there?
Linear rule.
The linear rule, which gives me minus 4. And what happens to the negative 4 at the end? That's 0. You don't have to write the 0. If it makes you feel more comfortable right now to do that, that's okay. But then you'll do one step where you don't write it because adding 0 doesn't change things.
Does it matter if, like, whenever I look at the 4x, I view it as a power rule? Like, if I keep doing that, will that mess up?
If you say it again,
Further down-
Chancellor?
further down the road. Like, whenever he said it was a power rule also, like the negative 4x.
Yeah.
I mean, is it okay if I just view that all the time, or will that
Yeah,
be
you can.
eventually?
You can. It just means you're going to have to simplify your answer to get you negative 4 at the end. So what you may have happen is sort of this intermediate step right here where you end up writing down negative 4 times 1 x to the 0, but then you're going to have to recognize that the x to the 0 is 1. So in your final answer, it needs to look like negative 4 because that will simplify to negative 4. Does that make sense? Yeah. Yeah, but you can definitely think of it that way. It doesn't hurt anything. Okay, let's do another one. This is notation that I have not shown you before. Any guesses as to what it might mean? It does. It means second derivative. And I haven't told you what a second derivative is or what it means, but it works the same way as a derivative, except you do it twice. Okay? Now you might notice that the notation looks a little funny because the 2 is here, and it's not the same place in the top and the bottom, right? It's a little funny. This is read as the second derivative of f with respect to x twice. So you're doing two derivatives. Both times it's a derivative where x is the variable. That's all that says. So the notation looks a little different. However, in order to do this, I still have to find the first derivative. which with the notation they're asking me to use or using in the problem would be df dx. Now, over here, x to the 6th is in a form that uses a power rule. However, the 5th root of x, yeah, I don't have any radicals in that notation. How can I rewrite the 5th root of x to make use of the rules I do have? Yeah, this is x to the 1/5. You guys remember that? Okay.
Is it incorrect to write f double prime?
No, it would be fine. I'm just going to use the notation the problem with used, that's all. Yeah, so if you want to, you could call this f prime of x. But it's the same thing as df dx. All right, so what's the derivative of x to the 6th? 6x to the 5th, which is a beautiful thing. How about the derivative of x to the 1/5? 1/5 x to the what power? -4/5. Very good. So you have to remember you're subtracting. You're not just, sometimes people want to put -1/5 on that one sometimes. You have to subtract 1, so you have to have 1/5 minus 1. Okay, so I know that you guys know how to deal with fractions. They may not be your absolute favorite, but that's something that you've certainly mastered at some point or you wouldn't be in calculus. Okay, so if it means you need to write it down to remember or do anything like that, that's fine. This is x to the -4/5. Now, if I were stopping here, I would deal with the fact that I've got the negative and the power is a fraction and all that stuff, but I'm not supposed to stop here. I'm supposed to be finding a second derivative. So I'm not going to do anything yet. I'm going to find df dx 2. I'm going to find the second derivative. All right, so what's the derivative of 6x to the 5th? 30x to the 4th. Very good. How about 1/5 x to the -4/5? What am I going to get there?
-4, -25, x to the -9.
Right. Okay, so the -4/5 gets multiplied by the 1/5, which gives me 4/25, and negative, just multiplying fractions. And then my exponent, which was -4/5, I subtract 1, and I get -9/5. Okay, so if you need a piece of scratch paper, if you want to use your calculator to do the subtraction, I don't care how you do it, but you're going to do the subtraction and the multiplication with those fractions. Okay? The problem started out with radicals, and they were positive, which means the problem needs to end with radicals that are positive. So there's a couple of ways that you could write the answer. The first thing to recognize is since it's a negative exponent, I'm going to put it down in the denominator to make it positive. The other thing to recognize is since I still have an over 5, that's still a 5th root. So I'm going to have 4 in my numerator, 25 in the denominator, and a 5th root, that's a 5, of x to the 9th. You can leave it like that if it bothers you to have the x to the 9th, which is a bigger value than the 5th root underneath there. Or if you're looking in the back of the book, what you may see them do is write down still the 30x to the 4th. They may actually write 4/25x 5th root of x to the 4th. And that's just a simplification of radicals. I'm not asking that you have to do that. But if you're looking in the back of the book, you should be able to make amends to the fact that that's the same thing. Right? And the reason that's the same thing is because 9/5 is 1 and 4/5. So the 1 comes out. That's what's happening. Okay? So either of those answers, if it were me, I would just leave it like this. Yes?
So your negative follow through, I'm a little confused. Because on the first you have -4/5,
Mm-hmm.
right?
Right.
Which is, you took the first derivative out, right? So that's positive. But then you move down, and you multiply it by negative. Oh, okay.
Did you find it?
Yeah.
I think we've got our signs correct. So we had a positive 1/5 that gets multiplied by the -4/5, so we had -4/25. And we didn't take any more derivatives after that. If we did another derivative, it would change signs again because we'd be multiplying two negatives together. And we can do this in theory all day. I mean, like we could do it again. We could do a third derivative. We could do a fourth derivative. There's nothing specific that says choose the maximum or anything like that. Your book doesn't go crazy with it, but just recognize that we could repeat this process if we needed to. All right, we're going to do another one. This one has a little bit different kind of a question. And the question has phrases that we haven't, one phrase anyway, that we haven't encountered. This says, use the given position function, which we did see that happen. We talked about that back in section 2.1, to find the velocity. So what is finding velocity asking us to do? Speed, and speed and velocity both are going to mean this is the first derivative. Now, when we did it, of course, in section 2.1, we did it using limits. Well, now we have a simpler way to do it. So we're going to be able to use these rules instead. Acceleration I haven't